Okay, we are ready. You can go whenever you want.
All right. Thanks. Thanks to everyone for attending the technical session number 2 of this HDR-Nets workshop 2020. And the session is titled Machine Learning for Networks. I'm the session chair for this session. I'm Dan Pei from Tsinghua University. And in this session, we have 4 papers, 3 technical papers, and 1 invited talk. And we have the first paper, a constrained reinforcement learning-based approach for network slicing. And we have second paper, automated saturation mitigation controlled by deep reinforcement learning. And the third paper, MoGAN, GAN-based next POA selection for proactive mobility management. And the invited talk, machine learning for distributed dynamic resource allocation in 5G networks. So we are gonna start with the first talk. I'll stop the sharing, and Yongshuai, you can start sharing while I'll introduce you. So our speaker is Yongshuai Liu from UC Davis. And Yongshuai is currently a 4th-year PhD student at UC Davis. And his research interests fall into reinforcement learning and networks. He currently focuses on real-world reinforcement learning problems, including constraint, sample efficiency, etc. Now, let's welcome Yongshuai for his talk. Okay. Okay, Yongshuai, you can start.
Okay, yeah, thank you all. Okay, yeah, thank you all. So, your voice kind of comes and goes. Yeah, I'm not sure if the problem on my side or the others have the same problem. But if you have any problems, I mean, if my voice not clear, please let me know. Okay, hello everyone. I'm Yongshuai from UC Davis. Today I'm going to talk about our recent work on 5G network slicing. So, and how we handle it with the constrained reinforcement learning. This is a co-author work with Professor Ding and Professor Liu. Okay, so with the increase of mobile network, we face strong diversification of services. For example, we have the autonomous driving, Industry 4.0, virtual and augmented reality, Internet of Things, etc. So those services are characterized by different performance, functional, and operational requirements. Therefore, they demand the network to be more flexibility. Because of the lack of flexibility in existing network, independent initiative or dedicated infrastructure solution had been developed. For example, 3GPP had developed a LT-specific mic that can coexist with general purpose mic. The industry has developed a specific architecture for extreme reality. So such solutions seems to work, but they're clearly highly expensive and inefficient. So to address this issue in 5G and future networks, network slicing enabled by the network function virtualization and the software-defined network is considered as a promising solution for the flexible resource allocation. So basically, the network slicing creates a multi-virtual network instance named network slices. So it can service isolation and guarantee on the top of common physical infrastructure. So the resource allocation problem in network slicing is provided the required service isolation and the guarantees. So in our work, we are trying to handle the network slicing problem with reinforcement learning. So the number one question we may ask is why we use a reinforcement learning instead of the traditional optimization-based approach. So we have 2 reasons. So the first one is the traditional optimization approach acquires accurate mathematical model with parameter node. So this is often very difficult to achieve in practice, especially with the increase of the complexity, scale, and the service diversity of the 5G and future network. So furthermore, constraints from the physical system and the service demand are prevalent and complex, such as the latency requirement or the service level agreement, which will furthermore increase the difficulty in modeling. So additionally, the network environment is affected by the location, the geographical property, or mobility, etc. All will lead to it's difficult to measure and model. So because of those reasons, it's very difficult to obtain an accurate model of the parameter node in the real network, and on which this is a traditional method replies. So second reason is the traditional methods do not adapt to hidden structure in the network due to the lack of knowledge and subsequent ability to explore and learn from the system. For example, when a user, when he experiments with the quality of the service, he may decide to not use the service again, or at least with a reduced frequency. So such hidden structure can significantly affect the user experience and the network performance, but are usually not directly observed or modeled. So because of those two reasons, we are trying to explore a reinforcement learning-based approach in this work. So this is the framework of our method. So basically, we have physical infrastructure on top of it, and we have network slices. And in this case, we consider three different network slices. We have a network slice manager, which makes a decision on its resource allocation. It takes input from the policy engine, and this part is what the reinforcement learning algorithm can provide. And this framework can apply to a general network slicing problem, including the radio access, or edge, or cloud, or cloud networks. So, but the key part we are focused on is the policy agent, how to learn a reinforcement learning method to provide the resource allocation. To bring the reinforcement learning, especially the deep reinforcement learning, into the network slicing, there are many challenges. In our work, we are focused on the constraints. So we may know for the typically reinforcement learning problem, the goal is to maximize the reward. However, in the real network slicing problem, in addition to maximize the reward, we also need to satisfy certain constraints. To satisfy those constraints, we formulate the network slicing problem as a constraint markov decision process. So let's first look at the typical MDP framework. Most people may be already familiar with this framework of MDP. See, we have a state, and given the state, we take action. We receive a reward, and we transmit to the next state. Here, we also have a discounted factor gamma, and our goal is to learn our policy pi that policy pi can decide action given a state, and they want to maximize the overall cumulative reward. This is the typically MDP. So in the typically reinforcement learning, we face an MDP without a known system model. So we need to integrate with the environment. And for the in the deeper RL, there's a few popular algorithms are developed to solve the MDP, such as reinforced TFPO and PPO. So now let's focus on how can we formulate the constraints. So in addition to the reward, given a state and action pair, we also have a cost C. So now our objective comes to, in addition to maximize the reward defined here, we also need to satisfy certain constraints. So we consider two types of constraints in our work. The first one is a cumulative constraint. So the cumulative constraint is the sum of constraint value from the beginning to the time being accumulated. For example, in network, we may the reward may be the through output. We want to maximize the overall throughput, but we also need to satisfy some constraints like the user experience over time. Okay, we also have another type of constraint. We call it instantaneous constraint. So it means in each action, when we take the policy, in each action, we need to satisfy certain constraint in each step. So for example, in the network, when we want to maximize the video quality for users. So at the same time, instantaneous constraint is the bandwidth allocated to all users cannot be higher than the overall bandwidth resource we have. Okay, to illustrate our method, we will consider a case study next. So here we consider a radio resource slicing scenario based on our previous work as a case study, and it can be extended to a more general case easily. Say we consider three types of users, basically three network slices. One is the video, another is the wave IP, and the third one is URLC. So we consider a time slotting system in the simulation, and each time slot is 1 second. At the beginning of the time slot, we assume we can observe the state, so which is number of active user in each network slice, and we can take action. So it's basically the action is the bandwidth we can allocate to each type of network slice, each type of users. So the overall reward we are using in the case is we consider the overall output for all slices. So we also consider these two type of constraints. So the cumulative constraint is the user satisfaction over time. We define the user satisfaction at each time slot as follows. So it's basically a bandwidth allocated to this user divided by the bandwidth it's required. So of course it cannot be larger than 1. And we also consider two types of the instantaneous constraints. The first one is the in-place constraint. So basically it's a bandwidth allocated to all network slices. It cannot be more than what we have. And third one is the in-place instantaneous constraint, which is the latency requirement of the users. We may obtain the latency from the buffer queue. So it's worth mentioned over here is in our work, we consider a dynamic hidden structure. So users of each network slice may arrive and depart follow a no person process. But furthermore, the arrive and depart rate depends on the user satisfaction. So this part is probably the key reason why a learning-based approach can potentially fall from the traditional optimization-based approach, because this structure is hidden, and for the traditional method they cannot learn, but for the reinforcement learning method they can learn the hidden structure. Okay, so now we formulate our problem to this. So we want to maximize the overall reward, which is the zero output in your case, and we also have three kind of constraints. The first one is the cumulative constraints, is the satisfaction ratio. When we also have the bandwidth allocation constraints. This is the explicit instantaneous constraint. We also have the implicit instantaneous constraint, the latency requirement. So to handle the cumulative constraint, we propose a method, we call it interior policy optimization, so IPO. And to handle the instantaneous constraint, we handle them with the safety layer method. So next, I will introduce those methods. So IPO is a method we propose to handle the cumulative constraint. So in the first, let me introduce the little view. So in the little view, there are two types of algorithms that can solve the cumulative constraint. So one is called the Lagrangian relaxing method. So where we want to maximize the reward or minimize the magnitude of the reward. And at the same time, the lambda is the Lagrangian multiplier, and we put a constraint into the optimization framework. Then we can optimize this with as a unconstrained optimization. So we will adapt the appropriate Lagrangian multiplier. The problem for this approach is typically is very sensitive to the initialization of the hyperparameter lambda, and specifically it will change over the learning process. So and also we often see the variation, the large reward and constraint variation during training. Another algorithm is called the CPU, constrained policy optimization. It's a trust rhythm method for constrained reinforcement learning, which approximately enforces the constraints in each policy update. It uses the optimization of the constraints to predict how much the constraints might change after any given update. And then the truth update that will both improve the performance while keep the constraints cost below their limitations. The limitation for their approach is very complex to compute and implement. So now let me introduce our method, the IPO. The basic idea for the IPO is simple. So just as its name suggested, so the intuition is we want to add a constraint as a parent function to the objective function, So if the constraints satisfied, the penalty added to the reward is 0. Otherwise, the constraint goes to negative infinity. Okay, in other words, this is the ideal penalty function we want. If the constraint is satisfied, the penalty is 0. So otherwise, the penalty goes to negative infinity. So, but in practice, this one, the ideal case, is not differentiable. It's very hard to compute. So we introduced a log variable function, which is a differentiable approximation of the ideal case. And here we illustrate the idea. So the dotted line is the ideal function, and the green line and the red line are two approximation of the log variable function. So with different hyperparameter t over here. So one is 20, and another is 50. So here we use a penalty function, so the log variable function. So we convert the constraint optimization problem to an unconstrained problem. So the first part is the objective function, and the second part is the penalty. And then we use for the first part, we use the standard PPO to solve the problem, where the PPO does a clip so that the policy does not change too much, and it can guarantee each time the policy will improvement. So this is our method to handle the cumulative constraint reinforcement learning. So compared to the Lagrangian relaxing method, we know the cost of this t can be fixed hyperparameter, and we do not have to change it over time. Also, in practice, actually, we also developed an adaptive one that t can change over time, so that is much less sensitive to the hyperparameter. So we can also show that the maximum gap between the optimal value and the constraint optimization problem and the IPO is bounded by m over t. So which is m is the number of constraints and t is the hyperparameter of the log variable function, as we showed earlier. So in summarize of the IPO, so we propose IPO to handle the cumulative constraints, and the IPO outperform a state-of-art method. It achieves monotonic improvement on the policy, so which is a property inherent from the PPO. It can also handle the multi-constraints. So because in practice, we do not have only one constraint, so we maybe have a lot of constraints together. So the IPO can handle the multi-constraints. It's easy to compute and implement, and the hyperparameter is easy to do. So another thing is it can also incorporate with the instantaneous constraint easily. So we will show next. So the idea of the solve the instantaneous constraint is introduce a sixth layer to the policy network. This is the idea borrowed from the literature. So basically at a given state, the original policy will give us a set of action. So we give us a set of action, but this action may be infeasible. I mean, maybe violate the constraints. So we put the action into a safe layer, and the safe layer will generate a new action, new policy, so that the constraint can be satisfied. So far, for the explicit instantaneous constraint, basically the bandwidth constraints, we do it in a simple way. We proportionally scale down the bandwidth required if it's more than the total we have, so it's easily done. So for the latency requirement, which is the implicit, we use the projection idea here, and the idea is also simple. Say we have learned the function of the latency, and we want it to be below a given threshold. So we find new action A, and the action is as close to the original policy. So, but the new action should satisfy the constraints. So this is where the safety layer is working. So next we will present the evaluation of masters. So we consider the traditional baselines where we evenly allocate the resource based on the user numbers and the packet number of traffic demand. Because we do not know the hidden structure, so this is really what the traditional optimization framework can give us. We also consider a typical reinforcement learning method PPO, but without consider the constraints. So in the first figure, all the figures, the x-axis is the time. how long we have been simulating, and the y-axis for the first figure is the accumulated output. So in the first figure, the higher the better, of course, and for the second figure is the cumulative constraints. The lower the better, and this is the constraint threshold we have. And for the third figure is the latency. The implicit the instantaneous constraint. The threshold is clear, but maybe it's not too clear. So overall, I want to say we can see our proposed algorithm the green curve can achieve a pretty good overall performance, and it can satisfy the cumulative constraint and the instantaneous constraint. So in summary, in this work, we talk about why we should use the learning-based method in network slicing resource allocation, and then we formulate the network slicing problem as a constraint reinforcement, constraint MDP. So we also propose IPO, which can handle the cumulative constraint. We also introduce a safety layer to handle the instantaneous constraint. So there's a lot of other challenges that if we want to apply the reinforcement learning method to in real world. So the first challenge is sample efficiency. We all know training a deep reinforcement learning method algorithm is very expensive. It requires a lot of data. And so in the network, how can we get such data, especially suitable data to training a policy is a challenging issue. So we have to improve the sample efficiency. So another important issue is trustiness of the policy. So network operator is unlikely to adapt a black box policy without knowing what is going on. So it's clearly very valid question. So there's two main components in this part. One is interpretability. So can we explain a policy to operators and let the operator understand what is going? So a related part is safety. So how do we know this policy is not going to generate undesirable results or reach to a dangerous state? These are related questions. So there are many other challenges, but there are two key issues we need to consider. Yeah, okay, this is our work. So thanks for your attention. So we can go to the Q&A session.
All right, great. Thank Yongshuai for the interesting talk. And any questions from the audience? All right, so I will start with the question. So Yongshuai, okay. I understand that what you presented is about how you do your work in the context of this radio access network. Do you see your approach can be generalized to maybe the core network or maybe computing server, this kind of resource allocation?
Okay, so unfortunately we didn't do that, but so what we're focused on is the algorithm side. I mean, so we think we can still apply it to the core network or general case, because the algorithm is the more general algorithms. But yeah, indeed, I have to say we didn't do the experiment on the more general case.
All right, thank you. Any questions? Any more questions from the audience? If you want to ask a question, just unmute yourself and ask the question. So, all right. Another question that I have, because deep reinforcement learning, as you previously mentioned, is kind of slow to converge in general. How do you think, how fast is your training, your algorithms training, and how feasible you think in reality such a training speed?
Okay, yeah, indeed. So the skill art of reinforcement learning, yeah, indeed is sample inefficiency. It's so, for example, for the Atari game, it requires medium data to get a good policy. It's almost impossible for the real world problems. So, but we have some other tricks to improve the sample efficiency. So the first one we can do, and we already did, is use a domain knowledge. Say we assume we have the expert knowledge. Say we have already have the policy from the expert, and we can start from that policy. So because we already have that policy, and the reinforcement learning can improve that policy, so it cannot be worse than the previous. I mean, we start from the terminology and learn an initial policy. It's kind of we use a one-step policy, then we can learn a policy quickly, batch policy quickly. So there's also some other direction to improve the sample efficiency. Say, for example, we do a batch exploration. So this is the work I'm doing now. And also some other things, for some other related question is if we can learn the model from the environment. So even we say the reinforcement learning method do not have the more accurate model, but we can learn the model and let the model to help us to improve the sample efficiency. Yes, there's other topics. Yeah.
Great, thanks. So for the sixth time, and I think that's the end of this talk, and let's thank our speaker Yongshuai again. All right, thank you. And now, Elkin, if you can start sharing your screen.
Yes.
Okay, so I will introduce Elkin. So Elkin August is a PhD student in Télécom SudParis Institut Polytechnique de Paris, in partnership with Orange. He has a master's degree in architecture and engineering for the Internet of Things from IMT, and a bachelor degree in EE from the Distributed University of Bogota. He's interested in the automation of computer network for security and the quality of service, and developing tools to accomplish this task. And there it is. So Elkin, you can start.
Okay. Can you hear me well? You can see the slides and
Yep.
me as well. Perfect.
And
okay.
Can you turn on your camera as well? Turn on camera so that audience can see you.
It's already turned on.
Oh, okay.
Yep. Okay.
Thank you.
So yes, well, welcome everybody. Thanks for being here. Thanks for the introduction. So today I'm going to introduce you to present you my article.
Yep. Sorry, Elkin, sorry for interrupt. You haven't turned on your camera yet. The screen is shared. Can you turn on your camera so that the audience can see you presenting the camera of your computer?
Sure.
Start the video. Yeah.
Okay.
Yeah, perfect. That's right. Okay, great. Thank you. Sorry for the interruption.
Oh, it's okay. Don't worry. Okay. So yes, so we're saying today I will present to you my article, Automated Saturation Mitigation, Controlled by Deep Reinforcement Learning. Well, I took a more practical way. So I will start with an introduction. Then I will show you the problematic that I faced, the proposed solution, the experimental results, and I'll finish the presentation with some conclusions. So nowadays, recent developments have shown that automation and machine learning have proven to be helpful in network infrastructures, mainly because they can optimize security, management, and performance. Particularly, there's something interesting here, and it's that this will allow a transition from error-prone and time-consuming manual manipulations as actions that are taken by humans that can be replaceable for more refined automated actions. This could help internet service providers with the challenges they face nowadays in the massive content delivery scenarios. We have content delivery networks, for instance, or CDNs that have that are main players, fundamental players in these scenarios, because they have control on how content is delivered by their geographical distributed cache servers. So mainly these dynamic and complex delivery strategies that use CDNs make that ISPs turn into these dump pipes because they lack control in these delivering scenarios. This can cause link saturation and lead to different types of problems, from users not being able to access services to packet dropping causing BGP session termination, for instance. Now, a graphical way of seeing the problem is this one. We have an ISP autonomous system with, in this case, is announcing 3 prefixes, and it's connecting to 3 cache servers directly and indirectly. So at some point, the direct connections, direct links with servers, with cache servers, are going to be at the top capacity. So the content delivery network is going to change the configuration, and it's going to make the remote cache to be the one that is sending traffic to the autonomous system. So the prefixes are going to be receiving traffic from this remote cache. Now the ISP-AS try to have some control on this procedure. So it's going to try to load balance the traffic by announcing the 3 prefixes on each link. This would sound a little bit logical from a certain point of view. However, thanks to the BGP configuration, so the traffic is going to go through the best path based on BGP, and this in this case is going to be the link with the autonomous system X. So this load balancing scenario doesn't work for the ASP-AS. So something that can be done at this point to solve this problem is not to try to load balance, but to load share the traffic that is entering the autonomous system. And this can be done by announcing 1 prefix per link in this case, which is going to force the traffic being sent to a specific link, to a specific prefix, sorry, to enter through a specific link. Now, this seems simple at this point. However, when you go to a real case scenario with hundreds of links and thousands of prefixes, then humans are going to be able to perform well in order to redistribute prefixes in a dynamic changing scenario of a core network. So this is why automation and reinforcement learning seem like an interesting solution to this problem of re-announcing prefixes to share the load. In order to do this, we need to have access to the routers, more specifically to the border routers of an autonomous system, in order to change the configuration and re-announce prefixes. So this is the general architecture of the solution that we envision. And there's a monitoring block, for instance, that is going to be taking measurements from the network frequently, and is going to store them in an event stack. Then there's going to be a reasoning block. There's where our reinforcement learning is going to be. That is going to take this measurement and is going to create a representation of the state of the network. Based on the optimization of this state of the network, of this representation, the reasoning block is going to choose an action that is going to be deployed into the network. Well, then we have the orchestration block that is going to coordinate this deployment of the action. And finally, an execution block. This is more a technical point of view. The execution block is going to connect to the devices and is going to implement the action. So zooming into the reasoning block. Reinforcement learning, we chose to use reinforcement learning as our method to approach the problem because it's naturally oriented to automation because of this closed loop in which it works. And more specifically, we work with deep reinforcement learning because of the the large state space that we work with. And even more specifically, we use deep Q learning. Now, regarding the states and the actions, which are a fundamental part of the problem. So for the states, so we're going to continue working with the image that you see on the left. We have 3 links. So we're going to take the maximum capacity of each link at a specific time. We're also going to take the number of prefixes that are going to be announced at a specific time at that link or on the 3 links, and also the volume of traffic that is passing through that link at a certain time. Now, regarding the actions, we're going to move prefixes from one link to another. We can do this by like one link or by batches of prefixes, one prefix or batches of prefixes from one link to another. So, for instance, if you take the first action, it would be move prefixes from autonomous system X to autonomous system Y. Working with reinforcement learning, we have reward functions that we want to maximize. We have 2 reward functions, a balanced reward function. I will explain that later in the presentation, how they work. That it's the simplest of the 2, and we have a priority aware reward function that takes into consideration like more real case scenarios where autonomous systems and internet service providers need to prioritize some links over another links based on the type of links they have. So specifically for our experiment, we use 100 prefixes, and each prefix is responsible for 1/100th of the total traffic being delivered, meaning that all the links are equal to each other in terms of traffic. One prefix is only announced, or one link at a time. This is the base of prefix load sharing. And well, the initial percentage of prefixes per link is set randomly, but making sure that saturation on exactly one link arises. This is a condition set for being, well, so we can compare actually the different algorithms that we use. You'll see that later. And so we have the capacities, as I mentioned earlier. These are the capacities that the internet service provider is going to set for each link. So for this experiment, we set 20, 30, and 50%. For the links, the ASX, ASY, and ASZ. Finally, we have the traffic that is being measured every 5 minutes, resulting in 288 discrete time steps per day. Now, regarding the algorithms, there are 4 algorithms, or we call them algorithms. First of all, there's a no-function algorithm, which represents the situation when saturation arises. This algorithm does nothing, literally does nothing. It's just a baseline of comparison. Then we have the naive function algorithm, which is a straightforward automation of today's manual prefix load sharing, meaning that this algorithm is going to compare 2 links. And if there's saturation on one link, it is going to move one prefix from one link to the other link. Also, it's a baseline to be able to compare the performance of our reinforcement learning algorithms. Now, the balanced deep reinforcement algorithm considers every link equally when redistributing prefixes. So this algorithm uses the first reward function that I showed you before, meaning that if there's saturation on one link, it's not going to move prefixes first to one of the other links that is not saturated. It's going to consider the links with resources equals in that sense. So finally, the priority-aware deep reinforcement learning algorithm. It's going to check saturation on links, and it's going to prioritize some links in order to move prefixes first. You'll see that also in the results. So regarding the performance, we consider the cumulative traffic loss due to saturation and the cumulative number of actions taken per day on average in order to compare the different algorithms. These are the performance metrics. So we have the number of actions per algorithm and the traffic loss per algorithm after doing a session of 1,000 epochs for a validation. So we can start with a NOF algorithm, with no function algorithm. We see that there are no actions that are being taken because no actions are supposed to be taken. And we see that on the right, that for the traffic loss, this is the algorithm that has the highest traffic loss of the 4 algorithms, which is as expected. Now, using the naive algorithm, which is going to compare 2 links and move prefixes one by one, we see that the number of actions increased also as expected, and the traffic went down. So this confirms that this approach technically of doing something, doing the minimum necessary, it's going to work, and it's going to reduce already the traffic loss considerably. Now, when we see the reinforcement learning algorithms, first of all, the balanced reinforcement algorithm, we see that the actions and the traffic loss go down. It's really interesting because, well, it's the best performing algorithm, first of all, and like the actions also like went down. Like that's the number of actions you can take per day, so it went down considerably to 15 in order to keep the traffic to a minimum, the traffic loss to a minimum, sorry. Now, regarding the priority-aware deep reinforcement algorithm, if we see the traffic loss on the right, well, we see that it's not it is different from the balanced deep reinforcement algorithm and the naive. It's in between both of them, but it's not considerably a lot, comparatively a lot. However, if we see the number of actions, we see that the actions skyrocketed to almost the maximum number of actions that we can have per day, which is 288, meaning that adding an additional functionality to the balanced deep reinforcement algorithm, and all this additional functionality is prioritizing some links over others, which is of interest for internet service providers for financial reasons, or quality of service reasons. Adding this additional functionality is going to mean that we're going to have to invest resources in the number of actions that are going to be taken. Now going to making like, let's say, a zooming in again into each one of the algorithms, we can see how they behave in a period of 1 day. This is the same day for all the algorithms. First, we have the NOF function algorithm. We're going to analyze the blue line here, the blue traffic and the blue prefix distribution, which is the traffic and the prefix distribution for the link with the autonomous system Z. If you remember well, at this point, this prefix distribution and traffic distribution should be at 50% as established by the autonomous system. However, we see in the figure on the top left that the blue dashed line is close to 80%, meaning that there is almost 30% of traffic loss, if you want to see it like that. So this is where we see this NOF, where the traffic loss is coming in this NOF algorithm. So if we pass now to the naive algorithm, the figure B, we see that doing something, well, actually the algorithm is moving one prefix at a time, so we can see how the figure is going down for the dashed blue line. We see that the dashed blue line, which is the prefix distribution, starts changing when the traffic reaches 50%, which is the maximum capacity tolerated by the link. So only at that point, prefixes are going to start being moved, meaning that to reach a convergence point, it's going to take some time. So we're still going to have some traffic loss and some saturation while prefixes are being moved. Now, going to BDRL, the balanced deep reinforcement algorithm, we see that the prefixes are being moved at the beginning of the day, which is after training the algorithm, is what the algorithm learned from this environment and from this autonomous system. These are actually the optimal distributions that I need to reach, and I need to move and take these actions to get there. At some point, we see some oscillation, and that's due to a poor how to say it, a poor way of choosing how many prefixes are going to be moved at certain point, like choosing the number of prefixes are going to form the batch that is going to be moved at some point. So the priority aware algorithm, this is the most interesting of the four, because we see that at the beginning of the day, even when the traffic is low at the beginning of the day, the prefixes are going to be moved, like the 100 prefixes are going to be moved to the link with the highest priority. So just to clarify, the priority of the link is set of highest priority for the blue link in this case, the second highest priority for the green one, and third highest priority for the red one. So yes, at the beginning of the day, everything is going to be moved to the blue link. So when the day passes by, we see that the traffic starts increasing, and it's the time to redistribute prefixes. So at this point, the algorithm or the model knows that it has to move prefixes from this blue link to the green link, which is the second in priority. So this is solely based on the reward function that I showed you before. So it is interesting to see that actually the model learned how to optimize this prioritization, or the distribution based on this prioritization. Now, regarding the balanced deep reinforcement learning algorithm, I tried two additional case scenarios. For instance, what would happen if the autonomous system decided to change the maximum capacity of the links at some point? So I trained the model with some additional capacities or potential capacities, and I chose one at random while validating, and it just showed that the model is able to learn which action to take in this specific case if the autonomous system, the ISP, decides to change the capacity during the day. And finally, what would happen if there is a peak of traffic at a certain point? Nothing happened, which just told me, like, just shows that the algorithm of the model is able to work with the resources available in the network. But as at this point there is no resources available, everything is optimized, let's say, with the capacities that the internet service provider established. Then there won't be actions that are going to be taken to move prefixes to other links. Something interesting here for future work would be to actually implement additional actions like prefix dropping, which is only an idea, which is some of a critical action because it can impact quality of service. So it will be interesting to see what the model is going to prioritize, if dropping prefixes or not doing anything, for example. So some conclusions, like in terms of the feasibility of this of automating action to mitigate critical events in networks, well, we can say that it is possible. Actually, automating helps these critical events that are usually done by humans, and it usually is a manual, let's say, process. We can see also that machine learning helps to optimize this control. Now, regarding the agent and the deep reinforcement learning process, it is also feasible to use them to control the choice of actions in this specific saturation case scenario. Well, in this case, after seeing that is feasible, we see that the reinforcement learning agent can minimize the traffic loss and the number of actions at a certain point if we choose a good reward function. Now, regarding the future work, there are certain things that are still that I'm interested to do. First of all, is the stabilizing the prefix distribution. Maybe you notice that there are, like, for the both reinforcement learning algorithms, there are certain oscillations in the process. So there are certain factors there that I consider the source of this oscillation. So yeah, this is something that is going to be looked at, and also to adapt this to more real scenarios, because networks are very dynamic and change all the time. They're very complex scenarios to consider for reinforcement learning problems. So thank you very much.
All right, thank you for the great talk. And any questions from the audience? All right, I'll start with one. If you don't mind, can you switch to slide number 15?
Yes.
Okay, so I was wondering, so you have the time step on the x-axis. I was wondering, what is the absolute time, clock time, for each step? So essentially, I want to get a sense of how soon your algorithm can adjust to the traffic changes. So what's the absolute time? So for example, one time step on your x-axis correspond to 1 minute, 10 minutes, 1 hour, or?
Okay, gotcha. Okay. Yes. One time step here at this point corresponds to 5 minutes of a day.
Okay, 5 minutes.
Mm-hmm.
Okay. But that means that your algorithm actually adapt to the changes pretty fast. Okay, good. So as you already mentioned, I was wondering whether you can actually your algorithm work well for some more complex traffic pattern. So because let's say your one timestamp is 5 minutes, right? So I think in your algorithm you adjust to the changes within a few timestamps. That's like 5 timestamps. That means like 30 minutes or so. I wonder, how your algorithm can deal with traffic that change more frequently. Oh, it's not like this kind of smooth pattern, but more of a bursty traffic changes. So can your algorithm handle that? Because for reinforcement learning to convert to a solution, you need time, right? But what if the network condition itself change relatively frequently? How does your algorithm handle that?
Yes. Well, it depends on the change that you mean, because, well, the traffic changes all the time during a day, you can say. However, if you have these changes that repeat themselves, maybe you cannot see it with your eye, but analyzing it with some complex deep reinforcement learning algorithm, for instance, can show you that there are certain patterns that repeat day by day. Then I think it is possible to actually like follow these patterns in time and react to them. However, there are certain changes that need to be done, and it's the time step, for instance. Here is 5 minutes, which for some people will be a lot. Personally, I think that maybe 1 minute will be better. But however, that will be also a problem for BGP scenarios, because BGP also takes some time to converge. So yeah, we have to consider that, but I think it's possible. It is feasible. Yeah.
Okay. All right. Let's pause for a couple of seconds to see any comments, any question from the audience. All right. So, okay. So one last question from me. So I understand that you compare your solution with some naive solution, manual solution and automated manual solution. Have you considered some kind of a simple heuristic? Maybe whatever the idea, whatever the insight that you already got, and maybe come up with some heuristic. Certainly, heuristic supposedly running faster and doesn't need a lot of training. Have you considered that direction during our study?
No, not at this point. Actually, we're considering it for future work, but at this point, we like for this work, we didn't think about it. No.
Okay. All right. Great. Thank you so much, Elkin.
Oh, thank you.
So we are done for this part. Thank you. All right. So our next speaker is Boyun Jang. If you can start sharing your screen, Boyun. So our next speaker, Boyun Jang, is a second-year master student at the Sungkyunkwan University, Republic of Korea, and she is majoring in artificial intelligence. So Boyun, you can start. Thank you.
Oh, yeah, thank you very much. Can you hear me?
Yes, I can hear you.
Thank you very much. And I'm going to start with my presentation. My name is Boyun Jang, and I'm from Sungkyunkwan University. And this is the title of my paper. And I'm the first author of this paper. First, the current mobile networks are having high performance for the services like virtual reality with the commercialized 5G mobile networks. This 5G requires ultra-reliable, low-latency communication with under 10 milliseconds of mobility delay. Previous 4G networks are running under a reactive mobility management system, where users select the next point of attachment based on the signal from surrounding points. However, with the environment where frequent handovers occurring, this reactive mobility management can be a bottleneck for achieving the ultra-low latency in 5G mobile networks. Thus, proactive mobility management for handover, where next point is selected based on the prediction, can be a solution. Two things are required for proactive mobility management. First thing is next point prediction with high accuracy, and second thing is optimal decision for handover trigger time. For these POA prediction requirements, there are some challenges to deal with. First thing is about densely deployed network nodes, as this figure. Dense cell deployment can be a challenging thing because when handover occurs, so many points are existing while predicting the next point. Also, real-time prediction and decision algorithms are mandatory thing for prediction. This work is focused on the first requirement of proactive mobility management, that is, next point prediction with high accuracy. Thus, we suggest a next point of attachment prediction mechanism based on a generative adversarial networks. Before explaining about our proposed model, I'll briefly explain about some previous deep learning approaches for prediction. Among very many deep learning models, recurrent neural network was known as a prediction model for sequential data. However, basic RNN has the problem that gradient vanishing problem might occur. This is a problem that if the sequence gets long, the gradient becomes reduced to zero and learning becomes unable. This can make a long-term dependency problem where past information decays during training. To solve long-term dependency, long short-term memory, in short LSTM, was suggested and widely used as a prediction model today. However, the structure of LSTM is quite complex, and this can cause more computational cost. Gated recurrent unit, shortly GRU, is the simpler version of LSTM. The structure of GRU is less complex than LSTM. That is, it is computationally less expensive. Even more is shown better performance for less complex data. In short, GRU is available to solve the long-term dependency problem in RNN and also have a less computational cost than LSTM. Generative adversarial network is a framework that consists of two adversarial neural network structures, namely generator and discriminator. Generator receives the random noise vector and makes the generated fake output. Then discriminator tries to differentiate between the real data and generated data. Generator will be trained to fake the discriminator by making the generated data really similar to the real data. Usually, GAN is used as the data generating model because of the ability of generator to make the realistic fake output. However, the GAN can be used in other domains. For example, discriminator will obtain high classification ability, and by using discriminator as a classification model, it can have a high performance for classification like intrusion detection systems. Also, if RNN-based model is used in the generator, then generator can be used as a prediction model. To compare the basic LSTM structure and GAN, the performance of LSTM is limited to the availability of large amount of data while training, and this is not always in the case for cellular networks. GAN has three features like this, like useful feedback from adversaries and the training about distribution of data and various types of data available. And this can overcome the ability of LSTM. These are the reasons why our work used the GAN framework as a prediction model. Our proposed model, MoGAN, is the abbreviation of Mobility Prediction GAN. Training data is needed for MoGAN, And because MoGAN is using the GAN-based structure, some pre-processing is needed. That is, for the raw movement history data, which consists of sequence of points, some pre-processing should be added. First, the length of movement, the amount of points in each sequences should be matched in the same length, but in the raw data, it is different from each other, so we need to match the length. For example, if we decide to use the sequence length, the number of APs for each sequence as 5, then some of them with less than 5 points should be ignored, and some with more than 5 points will be divided in this way. Also, because there is no difference in the importance of each point should be transformed into n-dimensional vector. MoGAN is a GAN-based model for predicting next point of mobile devices. So it consists of two structures, generator and discriminator. Generator learns from the previous sequences and generates the next point. That is, generator is used as a prediction model after the whole training process. The role of discriminator is classifying between real and generated data. That is, real and generated POA sequences. And the classification result gives the feedback for generator and supports generator's predicting performance. This is the overall structure of MoGAN. Purpose of MoGAN is to predict the next point based on the information from previous POA sequences. So first, divide the whole sequence X to previous sequences and the next point to predict. Input of generator is the previous sequence, and generates the generated next point. This generated next point will be combined with the previous sequence, and then this is the generated data. This generated data goes to the discriminator and used as the input data, and then discriminator generates the output. With this output, generator and discriminator is trained. Also, the real data with previous POA sequences and real next point also used as the input of discriminator, and the output will be used as the output will give the feedback to the discriminator. This is the structure of generator. It consists of GRU layer with softmax output layer. This is the structure of discriminator. Some fully connected layers are used because they are suitable for classification, and the purpose of discriminator is classification. In the fully connected layers, the hyperbolic tangent is used as the activation function, and for the output, sigmoid is used as the activation function. While training, binary cross entropy was used as the error function. And training of MoGAN is divided into two steps. First step is the same procedure of training of normal GAN. That is minimax step. And the second step is the additional training step only for generator. If only first step, the training of GAN only exists, generator will be only trained to deceive the discriminator. However, the purpose of generator is to predict the next point, not only to deceive the discriminator. That is, generated next point should be same as the real next point. If generator is not trained well, then the discriminator's classifying ability will also be degraded, and this will degrade the whole training process of MoGAN. That is the reason why we added the additional step. Check the difference between the real next point and generated next point from generator. This generated next point should be the same as the real next point. So check the difference between them and generator is trained to minimize the difference between them. This step will make the generator to make the next step same as the real next step. That is, it will predict the next point very well. This is the algorithm. With the input and the error function with binary cross entropy, and for the n epoch, first train the discriminator. From this step, it is the first step for actually the same step with the gain where GAN is trained. And for the 8 to 9, it is still the first step and train the generator. And from the 10 to 12, this is the additional training step for alpha epoch. We evaluated the MoGAN with wireless network data collected in Panjo, Republic of Korea. It contains some handover logs collected from 2 months. And this is the configuration. First, we check the prediction accuracy according to different sequence lengths. If sequence length gets longer, then the accuracy also gets higher. But if sequence length reaches into certain threshold, the accuracy also becomes similar. And the maximum accuracy was 96.33% for 31 sequence lengths. Also, MoGAN showed higher accuracy than original GAN for every sequence length. Actually, the original GAN is meaning that the GAN which only have the training process of step 1. Next, we differentiated the iteration of additional training step. However, there was no difference for accuracy, and increasing of iteration for additional step means increasing of computational cost. So we can say one iteration of step 2 per epoch show better performance than others. Then we differentiated epoch. Highest accuracy for MoGAN was achieved at 4,000 epochs, while that for previous work of LSTM was achieved at 9,000 epochs, which is over twice than MoGAN. Also, MoGAN showed less training time and test time than LSTM. Performance of MoGAN with limited amount of data was also evaluated. In here, we can see that even only 20% of data is used, MoGAN showed above 85% of accuracy and showed above 90% of accuracy even if only about 50% of data is used. This is showing the availability of MoGAN in limited amount of data, which can be desirable in real systems. Maximum accuracy of MoGAN was 96.33%, as I mentioned, and it is saying that MoGAN can predict most of the handovers as this case. And this is quite high prediction accuracy. This prediction accuracy is one of the requirements of proactive mobility management. Also, time taken for predicting next point was 5.85 milliseconds, and this is less than 10 milliseconds. And this is saying that MoGAN is suitable for decreasing latency in real 5G mobile network systems. MoGAN is not only showing applicability for prediction in next network domain. This is suggesting improved method for data-based prediction. So structure of MoGAN can be also used in other domains, which can be an additional achievement of our work. The dataset we used is quite limited because it is the one we collected. However, our work is a proof of concept that is showing mobility prediction with high accuracy is available with GAN. Thus, we are going to extend our work by using more suitable dataset to show that the idea of a MoGAN is applicable for a real network system. There are two additional works we are planning to improve our work. First, MoGAN can be improved by other attention mechanisms. Also, we can extend the prediction ability of MoGAN from single step to multiple step. Thank you for listening, and if you have a question, then please tell me.
Right. Thank you for the good talk. And any question from the audience? So if you have any question, you can just unmute yourself and ask.
I had a question which I have also posted on the Q&A. So my question is actually, is it possible to apply the same GAN algorithms and GAN methodology to predict not just the next POA, but also the dwell time on the next POA? That is, how long are you going to stay attached to that POA?
If actually the structure of the generator that actually the generator is used as a prediction model. So if some modification is applied to the generator, maybe it can be also available. And I think this also can be a future work.
Okay, thank you.
Thank you very much.
All right, any other question? All right, so for the sake of time, we will move on to our next talk, and thank you, Boyun. All right, so Syed, if you can start to share the screen. And
thank you.
All right, thank you for contributing to this invited talk. So Dr. Syed is received his master degree and the PhD degree, both in EE from Cornell University in 1994 and 1997, respectively. His graduate research work was on the training of deep learning models, and since then, his career has combined the two threads of various communication research and machine learning at corporate research labs. For example, FutureWay and Docomo, Biolabs, and some startups, and industries such as mobile semiconductor. And Dr. Syed is now principal architect in the next generation system group at the Cable Labs, working on application of AI/machine learning in both wired and wireless communication system. Right. Thank you.
Thank you. Thank you, Professor Bay. I will begin my presentation, and thank you all for being present. As you can see, that I'm going to talk about machine learning for distributed dynamic resource allocation in 5G networks. This is work done in collaboration with my manager, Bernardo Huberman. We are both at Cable Labs. Okay, so this is the outline of my talk. I'm going to quickly go over the topic of resource allocation problems in 5G networks. I don't think it needs much introduction in a session such as this, but I will argue that given the new set of requirements and constraints that we have in 5G networks, that the traditional centralized problem formulations do not scale. Fortunately, my work has been done for me. Arguments have been mostly made by the previous speakers. They have made it clear, and shown other scenarios for which traditional centralized problem formulations don't work. But I will also continue with such an argument. And in fact, the proposal that we make for a solution to automate resource allocation at scale involves two principal components. The first being the use of AI and machine learning models for prediction, and the second being the use of market-based schemes to do distributed resource allocation at scale. And what we mean by these two things, I will show with an example of resource allocation to UEs served by a comp cluster. Now, I will hasten to add that this is work in progress, so our results are extremely preliminary. However, they do show the promise of such an approach, we think. Okay, so let's visit the topic of network automation itself. And like I said, probably everybody here is aware of the necessity for it. It is certainly now widely accepted that 5G will require network automation to greater or lesser extent, greater as time goes on. And there is a quote from one of the prominent equipment vendors, Ericsson. And for the purposes of this talk, we will focus only on the provisioning part of the resource allocation part of network automation. So specifically resource allocation itself. And as I said, with 5G, there are certain new requirements that that we want for any resource allocation algorithm to satisfy. It needs to be dynamic. It needs to be scalable to high loads, large numbers of cells and UEs. It has to support low latency because we will get a variety of new services that require these properties. And once more, I'm going to argue that the centralized allocation algorithms are too rigid, inflexible, and unlikely to scale. Okay, so again, what do we propose? An intelligent distributed resource allocation scheme. So, and like I already said, the two components are intelligence and being distributed. The intelligence permits allocations that are personalizable, localizable, and add resilience. And the distributed nature will allow scaling to large numbers of cells and users, support for heterogeneous services, devices with very different needs and capabilities. This will be very likely the defining feature of 5G. Will operate with low latency and are dynamic. That is to say, able to react to changing scenarios very quickly. And this by itself also contributes to resiliency. So why do we say intelligent? Because we propose to satisfy these requirements through the use of AI and machine learning models. And the distributed property comes from and also allows us to use market-based methods of resource allocation. And what we mean by this, I will come to in just a second. Okay, so let's apply to this example. A comp cluster transmitting to a UE. The details of the calculations, derivation, and model formulation are present in this paper. It's on arXiv. So here is an example of exactly what we mean, a diagram showing what we mean by this. I took this diagram from this paper because it's a better diagram than I would have been able to draw by myself. So, however, the precise scenario studied in this paper is not what we are studying. Now, why might we require a situation like this, where a comp cluster is required to transmit to UE, and we want to apply AI and machine learning as well as market-based resource allocation schemes. We feel this may be called for if there's a fast, temporary additional resource assignment required in order to handle some abrupt change, either in the environment or in the demand. Now, what do we mean again when we talk about market-based comp resource allocation? Well, what we mean is that each UE, so each user device, gets a certain budget, which we also call the wealth, to purchase resources. Now, in this case, say resources are bandwidth. The base stations in the comp cluster are the sellers of that resource. The UEs are the buyers. Now, when we say they're buyers, they're actually, they don't buy outright for ownership. They lease for a limited time. So any purchase of resource from base station is only for a limited time. Now, perhaps more importantly, the UEs are strategic actors, meaning to say they're not just takers of the price set by the base stations, but the UE's actions even help to determine the price that the sellers can charge and set. Also, the buyer's actions influence the actions of other buyers. In fact, buyers and sellers are each trying to maximize their own distinct utility functions. And what are these utility functions? Now, we took the utility functions from this other paper published in 2016, and we're using the same name as was used in that paper. So we call them bid packet utility functions. As you can see, the UEs, the buyers, and base stations, the sellers, have distinct utility functions. Both are quadratic, though, in the commodity being sold, which is bandwidth, right? Note, however, that each has a specific parameter, B in the case of the UEs, the buyers, and this is something that measures the need or urgency of the buyer for that bandwidth. And A in the case of the base stations, that's a measure of the importance to the base station of conserving bandwidth, meaning to say there is a cost to the base station, even of selling bandwidth right now, because it may be more profitable for the base station. Remember, the base station's utility is its profit. It may be more profitable for the base station to hang on to the bandwidth, not sell it now, and sell it later at an even higher price when perhaps there is congestion in the network and bandwidth is in greater demand. So these aspects are modeled by, like I said, the parameters A and B. But A and B will have to be estimated or predicted by the machine learning models. I will go into a little more detail as to exactly why we need machine learning models for this. But for now, let's continue with the analysis of the market-based modeling. So at equilibrium, supply will equal demand, and you can solve for what the price per unit of the commodity being bandwidth in this case, is. And it's given by this expression here. Where what is the bid? The bid actually happens to be exactly that fraction of the wealth that the UE is prepared to spend in order to purchase bandwidth. Okay, the UE has a need for bandwidth that is determined by the parameter B. It has a budget of W, and it allocates that fraction B of its budget in order to purchase bandwidth at this price. And it purchases precisely as much bandwidth as it can at that price. Okay, now note that to keep the UEs honest and to prevent them from bidding arbitrarily high, the budgets, though they can be in virtual currency for bidding and buying, they can't be entirely funny money. That currency has to be linked to real money or credit. So somewhere the UE really is being charged in a a tangible amount of resources or assets in order to purchase the commodity. Now note that bandwidth purchase transactions are between individual buyer-seller pairs. It maximizes both buyer and seller utility at equilibrium. And because of the nature of these transactions, just being individual between individual pairs, they're fast, they're distributed, they're scalable to large numbers of buyers and sellers. Okay, so let's look at a quick numerical example. Okay, this is highly idealized, I will hasten to say right now. But let's look at it anyway. There's a bandwidth allocation only. There are 10 UEs bidding for bandwidth from comp cluster. There are 4 base stations. Each base station has 25 units of bandwidth. Okay, and we'll go with these abstract units right now instead of talking of real world physical units, because for the purposes of comparison between different schemes, the exact physical translation of an abstract unit to a physical quantity like hertz or megahertz doesn't matter. Now, all bandwidth may be used for simultaneous transmission. We claim that. Each UE has a default of 10 units of bandwidth. because there are 4 base stations with 25 units each, so a total of 100, 10 UEs, equally distributed. Each UE has 10, but it has a budget C to buy more, and this is important. More important, the budget is not replenished for over the duration of the simulation. Okay, and each simulation runs for, well, a certain length number of allocation epochs, but I'll go to that in just a little more detail in the next slide. The UE can use its default 10 units of bandwidth to buy, or it can use that, or it can purchase more from the sellers. Okay, and like I said, we completely idealize. We say one file length unit needs one transmission with 1 unit of bandwidth. More importantly here, this is work in progress. We are currently working on fine-tuning our predictors models, machine learning models for the quantities B and A. So for right now, we just take them to be IID uniform 01. So let's see what happens even with these significantly idealized scenarios. Note that we run for over either 100 allocation epochs or 1,000. Now, there are 10 units per UE and there are 10 UEs. So over 100 epochs, if they use only the default allocations, the total data transmitted would be 10,000, and over 1,000 epochs, it would be 100,000. But look how much larger the total data transmitted can be if the UEs are allowed to use their budget C to go out there and purchase extra bandwidth from the sellers, namely the base stations, right? So clearly there's no contest here. This you can make it much, much larger. Of course, the increase in total data transmitted over the default allocation is limited only by the size of the UE budget. When the UE budget is small, when it's given only 100 units, and then even over 100 epochs, the budget gets exhausted along the way, and it's not able to buy anymore. However, for these 3 budget choices we have here, 500, 1,000, or 5,000, we don't hit that limit. And that's when we see these huge gains. So I had promised to discuss the role of AI and ML in this scenario, for example, and they have a very important role to play. Like I said, we have these parameters B and A, and we said that they should be estimated or predicted using machine learning. Let's look at the UE first. There's a B prediction model. It's trained on the subscriber's usage or profile. So this is what allows for personalization. This is specific to that subscriber. However, this also brings up privacy issues. The model should be trained on the UE itself, because that's one surefire way to safeguard data privacy. However, suppose the user who owns the UE suddenly downloads a new application and begins using it. For example, the Whova application, it didn't live on my phone until today. Now, does the model know how to handle this new behavior by the UE? I may be using Whova for the first time, but there may be other UEs who have used Whova before. So if we could do some sort of privacy safeguarding learning across UEs, we could increase the resiliency of the network. And this is a job tailor-made for a form of learning called federated learning, which I'll discuss in just a moment. Now, let's take a pause and look at the base station side of things. It's very similar. There's an A quantity that you have to predict. And again, your model needs to know how to handle sudden changes in the environment. So again, this is something that you could probably address by using federated learning across the base stations. Okay, and I've talked about federated learning. What is that? Basically, it is a way by which a collection of local learners training copies of the same model on their local data can collectively train a global model without ever exchanging data itself. Instead, what they exchange is actually the model parameter updates. In fact, they don't even exchange it. They just send it up to a central controller, which weights them by the size of their local training data sets and sends back the updates. Now, should the update completely override the local model parameters that have been trained on local data? Probably not. This is a major open research question. The extent to which the global model should be mixed with the local parameter updates, because the local model trained on local data is indeed optimized to local conditions. But you need some aspects of the global model, like I said, just in case the local environment abruptly changes. And this increases resiliency. And as you can see, only model parameter updates are sent up, never the local data or raw data itself, and therefore privacy is maintained. Okay, so in summary, 5G network deployments at scale will require automation. I think that is widely accepted. And this automation in our proposal will be done by a combination of a market-based allocation scheme with machine learning-based prediction models. The benefits of this approach include the capability for personalization and localization and resiliency. And these will be facilitated by and accommodated via federated learning. And with that, I will conclude my presentation. Thank you very much. I will be happy to take any questions.
Great. Thank you very much, Syed. Any questions from the audience? Or is there any question on the Q&A session on WUA?
Can I ask a question?
Sure, please go ahead.
Please.
Yeah. Hi, Syed. This is Tamir. I have a quick question about the model, especially about the distributed part. So my understanding, maybe this is my misunderstanding, is that you have the user equipment and the UEs, and then you have base stations. So is the base station playing a role of coordinating between the UEs here, or it's a really fully distributed? Just trying to understand the architecture of the distributed here. What are the assumptions?
Yeah, well, what we feel is, well, in this particular scenario, each UE is basically purchasing from all the base stations in a given comp cluster. So the cluster as a whole, supports this market-based mechanism. The sellers are the base stations, of course. The buyers are the UEs. But transactions are bilateral between one UE and one base station. However, obviously, if that UE has sold, basically committed a fraction of its available resources to a given UE, then that base station doesn't have those resources to supply to the to the comp cluster itself. So the other base stations and the comp cluster controller must be aware of this fact.
I see. All right. Thank you.
All right. Any other question? I have a very quick question. You have model at the UE and you use the local data at the UE to do the training. I'm wondering whether there are enough data, sufficient data for the training at UE.
Very good question. Actually, this brings us to the long-running and always present issue of cold start, right? So, if you are say you just purchased a new device, right, and you've just started using it. Now, clearly, there's not enough data over there for this to be able to, to create a user profile, a usage profile, and then start to predict quantities like B, and then do these purchase things for you. So, what we are expecting is that this is where the federated learning will come in handy. If the network knows about multiple users such as you, and that have that have collectively trained a global model which can serve as a baseline. Then as soon as the new user join the network, the baseline model can be downloaded onto your UE. So again, none of this is going to violate any privacy requirements of data. And that baseline model will eventually be fine-tuned with your local data. But at least at the beginning, it should provide some baseline level of performance so that it can get you over the cold start problem.
Okay. All right. Thanks.
Thank you.
Okay. Any other question? All right. So we are running a little bit late anyway. So let's thank our speakers, Syed again, for the great talk. Thank you.
Thank you.
All right. So that concludes our session, this noon session. And I think there's going to be a 1 hour and a half of lunch break in Central European time. And our next session will be, I think, what is the time? 1.5 hours from now. And we are going to have another keynote, and